Please switch on your cameras. All I request you to switch on your cameras.
Thanks.
Yes.
So I can assure everyone that it's the last technical lecture. Tomorrow will be very light. I will mostly show you pictures and give additional examples. Okay, so just switch on your brain for last hour, and then it will be easier. Okay, so let me summarize what we've done so far in this replica computation. So, like I said, the goal is to compute the expectation of the logarithm of a random function, okay, where the randomness is this y. And the issue is that it's difficult to compute expectation of logarithms. So the way to get rid of this log is to use the replica trick. So by Taylor expansion, you realize that when you can convert the problem of computing this log moment into computing a normal moment, but at the price of making sense of what's the zeroth moment of this random function. And it's a problem that at the moment we're kind of setting aside, because we're starting the computation for integer moment, for which this is just a normal moment and everything makes sense. We don't need to think too much. And the point is that now that we got rid of this log that was stuck here, this kth moment can be computed, because if you write down z to the k, this is just this replicated integral, and that you can think of the normalization constant of the posterior distribution of independent replicas, right? Because this z to the k is just the normalization of px1 given y times px2 given y, k given y. Each of these p carry a z as normalization, and so the normalization of this whole product measure is just z times z times z, z to the k. So it's independent replicas, and this is the associated partition function. What will couple these replicas is, again, the fact that we can integrate out now the noise component. So we integrate y conditional on x star. So x star is there. So really, here I've not been precise enough. The expectation that we carried was really an expectation of yij given x star, right? And yij given x star is a Gaussian random variable with this mean and this variance here. So this is just a Gaussian integral, so you can compute it easily using the standard Gaussian integration formula. And we ended up with a formula that looks simpler. So now there is no more noise, and conceptually what we've done is go from a system in z to the k, apart from the fact that we're sharing this quenched randomness, this disorder z, the noise. And by integrating the noise, we gain the fact that there is no more noise anymore. So this is good. But the price you pay is that you obtain a new formula where now replicas are coupled. Okay, so there is no free lunch. So we get rid of something, but we pay the price of coupling these replicas. So now we have terms like this, where A and B interact, okay, in a pairwise fashion, and this term where the A's interact with the ground truth x star. Calling again, just changing notation and calling x star x0, we realize that this integral can be further simplified and made very symmetric. So we have this kind of exponent there with a double sum over a different than b and a double sum over a I different than j. So this is the summation in replica space over the replica indices. This is the summation over real space, the components of the vector. And now the goal is somehow to find ways to decouple these sums, is to linearize everything, okay? So the way to do that is to do like in the Ising model, is to recognize that now this exponent can be expressed in terms of statistics of x. It's not a generic function of x, it can be written in a more compact manner in terms of the overlap, the order parameter in physics language. So indeed, one can recognize that this double sum over I different than j can be written as a single sum to the square, okay? Up to a diagonal term that we remove to complete the square, but which is negligible, okay? So this we can then forget it. And when we have done this, we are at the same stage as the Ising model. We can define this kind of sufficient statistics that depends on xa and xb, it's just the angle between them. And so here we have this q square. So now we have re-expressed the energy of our system, this energy function, for the replicated system, not just the original system. We had to replicate to identify such a simple form. And now this energy is expressed in terms of sufficient statistic of an order parameter, okay? Perfect. So now we need somehow to decompose this integration over the so-called microscopic configurations, so the configuration space of our vectors, our replicas, into subregions corresponding to different value of this order parameter, okay? So it's, you decompose the space of microscopic configurations into macroscopic states. You remember the lectures of yesterday. But doing so, we need, basically we are coarse graining the system. We're going from a microscopic description to a macroscopic description. We zoom out and we are trying to express everything in terms of this overlap instead of the x's. But when you do so, you need to count the number of configurations of the x's that are in agreement with a certain value of this statistic, of this order parameter. So this is where the entropy enters into play. This is the energy, but now we need to count the degeneracy of configurations in agreement with a certain value of the energy, okay? Like we did in the Ising model, where we counted the number of configurations which have a certain magnetization. In the Ising model, we could do that straightforwardly, because it's a very simple model. It was a trivial combinatorics problem. There, it's more complicated. You have like a set of k plus 1 from 0 to k vectors, these replicas. You are trying to understand what's the volume of configurations they cover. When you are enforcing this vector to have certain angles between them. You are enforcing all the pairwise angles between them. These are these QABs. And then you are integrating over this kind of frame of vectors, and you are counting the number of configurations such that this frame is fixed, such that they have these fixed angles between them. Okay? So it's a complicated geometric problem. You cannot compute it so easily. So the way you do it is you start from the definition of what this degeneracy is, the entropy, which is counting the number of configurations of the x's such that their angles are fixed to some predetermined constant, this QAB. And of course, if you integrate over all these possibilities, you are just integrating over all the space of configurations, right? So you are plugging this identity that 1 is equal to the integral over all possible angles of this entropy into the replicated partition function. In this way, now this object depends on these predetermined angles, these QABs, and the only dependence in the x's is through this capital Q squared. But because of this delta constraint, here I'm allowed to replace this function of the x's simply by these predetermined angles. This is the same because they're equal by this constraint. But now the only place where these x's appear is here. Okay. And now I use this trick that I can rewrite this delta function in exponential form using the Fourier representation of this delta. Okay, so it's a very important and standard trick in physics, but very powerful. So I use this identity that somehow a delta function can be written as an integral with respect to an auxiliary parameter, a Fourier conjugate, x hat, of this difference here, which is this one here. Okay. So it's like if you're going to Fourier space, okay? Okay. So if you do so, you obtain this expression. Again, this is our energy, which looks very simple now. And this contribution, this whole exponential, is the entropic contribution. Okay? And then we have the integral over all possible angles and the associated Fourier conjugate that enforce by integration these constraints. And we have, of course, the remaining integration over the x's that appear only here now. And the point of all this simplification now is that we ended with an expression which is fully factorized over this index I, because this sum over I in the exponent becomes a product in an exponential. And this reference measure here is also factorized over I by hypothesis. It's a modeling assumption in this problem. So what we obtain is that we have a single integral that appears here, the power n, because this is just a dummy variable. So we went from high dimensional integral, which is not solvable, to something that looks much less scary because it's a one-dimensional integral now. Okay? And the price we paid to go from high dimension to low dimension is that we had to introduce the order parameters, this Q, to identify them, and to introduce the associated Fourier conjugate to write the delta functions in Fourier in exponential form. Okay? But really you gained a lot. You don't have any more coupled high dimensional integral. You have a single one-dimensional integral there. And the thing we need to keep okay. Yes, I was saying that now through these simplifications and the identification of the correct order parameters and the conversion of these delta functions in Fourier form, in exponential form, we managed to fully lower down the dimensionality of the problem. We went from high dimensional integral to a single one-dimensional integral to the power n. So we have decoupled in real space. Okay? But of course, another price we have to pay and to keep in our mind is that not only we had to introduce these order parameters, I will also call Q hat from now on an order parameter. But also we have to make sense of this integral at some point.
Sorry to disturb you. Is the screen visible to audience?
Excuse me. No, excuse me. Yes, I thought I clicked.
No, not visible.
I'm starting the screen now. Is it now? Yes, okay.
Yes, now it's visible.
Thank you very much. So sorry, I was saying that I will also from now on call Q hat an order parameter. So we had to pay the price of introducing these order parameters, and but what we gained is that we went from a very high dimensional integral of coupled variables, which were these replicas. There was this order which was represented by the noise in the data. Now there is no more noise. It has been integrated out. And there is no more high dimensionality. It's just a one-dimensional integral. We have factorized over the index that was growing to infinity, which is this I index, but it has been factorized entirely. Okay? So this is very good. But another price we have to pay in addition of these new variables that we need to integrate at some point is also the fact that we'll have to make sense at some point of all these formulas when k goes to infinity, right? You need to remember that here all this looks very nice, and because this k has been taken to be an integer, but in reality the replica trick tells us that at some point we need to take k going to infinity to 0. Okay?
Yes, Mr. Om Prakash.
Yeah, I just did, don't worry, it's fine. Okay, perfect. So yes, so let me now show the next steps. Let me open my notes. Okay, perfect. So now that we have factorized this high dimensional index I can rewrite all this as a constant. So the constant here that I'm talking about is just this 1/2 pi normalizations from the delta functions, but they will not matter at the end. Integral of dq hat, which really are matrices of size k plus 1 by k plus 1. And you see, if I have something to the end, this is exponential in n, so I will write explicitly an exponential. Exponential n log of all this integral. And this dxi, now the I index is not there anymore, so I can just integrate over a scalar. So this dx, the x now here will be just a scalar indexed by a. xa, xb minus qab plus lambda over 4 qab squared. Okay, and all this is in the big exponential there. Okay, and I will put, I will even put excuse me, I've done, I could have written something simpler. Yes, I can write, all the terms that depend only on q, okay, can be taken out of this integral, okay? They do not depend on x. So I can factor them out. I obtain dq hat exponential sum a different than b qab hat qab plus lambda over 4 sum of QAB squared. And then the integral, all this with the n to the power n, which is there. And then I have my integral to the power n, which I can write as the exponential of the log of n times the log of this one-dimensional integral. Sorry, it's a k plus one-dimensional integral, but the I index has disappeared. 0 to k dxa pxxa times exponential of sum over a different than b QAB hat xi, there is no more I, xa, xb. Perfect. So why have I written all this in this form? Because you see that what we obtain is something of the form dq hat exponential minus n, some action, so in physics we call that an action, that now depends only on the order parameters. So you see this action is defined by this whole exponent, where I factorize the n, and there is no more x. X is integrated here. So this is just a function of q hat. And so this function of q hat plus this function of q and q hat, I call it capital A. It's my action, okay? So the terminology action just comes from field theory, from physics, but it's just a name. It's a function of q and q hat, okay? What is important is that now I precisely have the form that I need to compute this integration, the final integration that remains with respect to q and q hat, by saddle point integration, or if you want, it's a advanced Laplace approximation. Basically, what I'm exploiting is that I have sums of exponentials with a very large exponent, and that the integral is again dominated by the largest. It's a bit more subtle. I should not say largest. It's a bit more complicated because one has to be careful. Remember that these q hats, when we introduce the Fourier representation of the delta function, they're complex numbers, okay, in reality. So really this A, this action there, is a function of complex valued variables, okay? And when you integrate an integrand of this form with respect to complex valued variable, there is no notion of mean or max, because these are complex numbers. So what you have to select, this integral, when n will become large, what you have to select is the saddle point. It means a solution for q and q hat that extremizes this action, such that its gradient is equal to 0, okay? If there are multiple solutions, you should select the one that, in this case, minimize this A, because we have a minus, so that the exponent is maximized. So among all solutions of q and q hat such that gradient of A is equal to 0, we'll have to pick the correct one. But so saddle point integration means this. You have integration with respect to possibly complex numbers of an exponential times an exponent which is very large, and you integrate like this. So it will be dominated by the sum. Okay? So we have the right form to finish the computation. Okay? Perfect. So the action here takes the form. Let me write it. Minus sum over A different than B, 0 to K, of lambda QAB squared over 4, which is this term there. Then we have minus QAB QAB hat, which is the coupling term here between the two types of order parameters. And then we have this integral there. And because I factorized a minus there, we have minus this integral. So minus log, we'll write it below, minus log of integral of dpx exponential sum of a different than b of QAB hat XA. X was telling us, so if I was telling us that the limit, now I also take the limit when n goes to infinity of expectation with respect to y of log of z was equal to the limit, and so this I can replace using the replica trick, limit when k goes to 0 plus of, and I'm going to use one of the three forms of the replica trick, which is expectation, log of expectation of z to the k over, and I will take a 1 over n there over nk. Perfect. So the expectation of z to the k is there. So it gives us lim when n goes to infinity, lim when k goes to 0 of 1 over nk integral with respect to q and q hat of exponential minus n, our function of q and q hat. Okay, this is the form we ended up with. So now I need to make an assumption to finish I will need to make two more assumptions that I cannot justify rigorously, okay, which are heuristics. The first heuristic is that I will assume that these two limits, they commute. I can exchange the order of these two limits, okay? So, and this I cannot justify. I can only justify a posteriori because I can prove with other techniques that the final result I'm going to show you is a theorem. But I cannot directly justify this limit at the level of this replica computation. But at the end it's true, okay? So let me put instead k here to 0 and the n here by commutation of the limits. And you see that now I am in position to compute this integral by saddle point. Okay? So this precisely can be computed by saddle point integration. So this gives me limit when k goes to 0 of the, so you see, saddle point means that this integral is dominated by exponential minus the extremum of this, okay? If we were integrating with respect to real variables, q and q hat, you could say that this integral is exponential minus n times the minimum of this function, meaning the maximum of this exponent because of the minus, in the case of real variables. But these are, at least q hat, they are complex valued variables. So it means that we are thinking in the complex plane. So in the complex plane, you need to take a saddle point. Okay, it's an extremizer. It means a point where the gradient vanishes. There may be multiple ones, in which case you need to select the correct one. But in any case, it will be a point where the gradient vanishes. something. There is another type of integration of this form, which are called the stationary. Wait, I have a blank. Another form of how is it called? Stationary. A stationary phase approximation. Okay, so you see, this integral gives exponential minus the extremizer of this. With this n will simplify with this n, and so what I get is limit when k goes to 0 of minus 1 over k extremum with respect to q and q hat of this action. Okay, so there is no more n. We got rid completely of n now. It's a variational problem that we need to solve over scalar variables. Okay. A priori, here so because I'm doing saddle point integration, I'm working in the complex plane. This saddle point that extremizes this quantity could be anywhere in the complex plane. So really, here when I'm doing an extremization, this q and q hat a priori could belong to C, and these are matrices, k plus 1 times k plus 1. So I will write the stationary condition. I will write the gradient of A equal to 0 and solve, and at the end I will realize that the solutions are real. So if you open a paper where people do this kind of computations, they never write this because they know in advance that the solution will be attained on the real axis. Okay, and the reason is that these quantities, they have a physical meaning. They really correspond to angles between posterior samples. They are not complex numbers. So even if you extend while doing the computation to the complex plane in order to use these tricks, saddle point integrations and things like this, at the end, it's a physics problem and solutions are obtained at real values of order parameters. Okay, so that's why physicists would never write this. But here I just do it for you to understand what I mean. Okay, perfect. Okay, so we can still simplify what is going on because you see, now it's a low-dimensional optimization problem in the sense that this k is finite and then we take it to 0. It's not growing with n, so it's low-dimensional. But still, what does it mean, k going to 0? First, what does it mean, matrices, you see? When k goes to 0, they become scalar. So this suggests that maybe I can reparameterize these matrices in an easier way. And so this is where enters the so-called replica symmetric ansatz. Okay, so the replica symmetric, and that's why these formulas, by the way, are called replica symmetric formulas, precisely because of the ansatz we're going to make there. So the replica symmetric ansatz is the assumption that the extremizer of this action, of this function, takes a special form, which is QAB equal Q for every AB, A different than B, and let's say Q, let me call it Q for A different than B, and V for A equal B. So it's a matrix of the form V and Q on the off diagonal, and it's k plus 1 by k plus 1. Okay? So, perfect, and same for Q hat, where you put a hat there. same form. Okay? So it's called replica symmetric because you see it tells you that these columns and these rows they are indexed by replica indices, by posterior samples. And it tells you that if you take replica A and B, whatever are A and B, their angle, the Q, will be the same. Okay? So what does it mean physically, this? Because again, this Q, we know what it means. This Q is this QAB here, which is the overlap between our vectors in high dimension, okay? The fact that we're saying that for any two replica, their angle is the same. So if you sample today your posterior measure one time and another time, and you repeat the experiment tomorrow, you sample again you sample it again twice, and you look every day like this, what's the angle between your posterior samples? We are assuming that it's always the same. So it concentrates. It does not depend on the posterior samples. So it's a concentration property, okay? And this you can prove also that it is true using other techniques. It's a whole field of mathematics to show this kind of concentration statements. Myself, I've worked a lot on this. It's very interesting. So here I will not justify it, but you can prove that it's indeed correct. That if you sample posterior measures multiple times and look at angles between vectors of posterior samples like this, it will be always the same. It does not depend on which samples you are considering. Okay? Of course, these samples must be proper samples of this measure. They must not be atypical samples, very rare samples. It could be that if you try this exponentially many times, this experiment, so very, very, very large number of times, at some point you see a deviation. But this event has a very small probability to happen. So it can be forgotten, okay? It has exponentially small probability to occur. Almost all the time, if you sample your posterior twice and look at the angle between the two vectors, it will be a constant, okay? And this constant is what we call Q. Okay, so this is what this assumption is saying. Instead, on the diagonal, it's the norm of a posterior sample. It's the angle between a vector and itself. So it's norm squared. Okay, which of course has to be different. Perfect. Making this assumption allows to greatly simplify the above formula. Because you see, in particular, where is our potential? Something like this becomes just Q times Q hat times K plus 1. And this, in this integral, in this exponent there, this QAB now has no AB anymore. So I can put the Q hat in front of the sum. And this term also simplifies. It just becomes K plus 1 times the same terms. Okay? So let's write it. With this assumption, the action is equal to K plus 1. We're almost there, I swear. It's almost finished. Minus 1 over minus, where is, yes, the action divided by K gives this. Okay, perfect. And now we can use again the same trick that we used to decouple at the end the I index, the high dimensional index. Look, we have a final coupling here. This is this term here. It's the coupling between the replicas, okay? It's a pairwise coupling in the sense of a product between XA and XB for every A different than B. you should be tempted, and you would be right here, to use again a Gaussian integral to decouple this exponent, to linearize this exponent. And this is what we're going to do. So I can rewrite using again the Gaussian formula there. Here. I can use it to convert the exponential of a square into a Gaussian integral. You see, this is linear in B. This is what I mean by linearize. This is quadratic in B, and this is linear in B. But the price to go from quadratic exponent to linear exponent is that you need to introduce an auxiliary Gaussian variable, okay, whose variance is inverse variance A is related to what is at the denominator of this B squared, okay? So this is the linearization trick. You can go from quadratic to linear at the price of introducing a further integration variable. It's similar to what we've done here. We had a function that was quadratic in the variables, and at the price of introducing a new integration variable, actually two, q and q hat, we obtained an expression which was linear in this is I. So you see, you can go always from quadratic functions in exponents to linearized version at the price of introducing additional integration variables. Okay, and this is a very important trick. Because you see, I have to do that in the sense that this expression, if I do not move forward, if I do not further simplify, I cannot make sense of it when k goes to 0. I need to take the limit k goes to 0 from the replica trick. But this is an integral over k plus 1 variables. I can only make sense of this integral when k is an integer. So somehow I need to do something before taking k going to 0, which is the final limit we need to take. So this is what I'm doing now. So this integral can be rewritten by the Gaussian integral, by the Gaussian integration formula, as log of integral product dpxxa. So let me first exhibit the square, q hat over 2 sum of a xa squared. This is my squared minus the diagonal term, which was not present, that I need to remove. And this is my b squared in the Gaussian integral formula. It's my b to the squared divided by 4a. So now I introduce a Gaussian variable to linearize this. This is the same. So really the Gaussian integration formula is used here as log of integral product dpxxa exponential q hat over 2. Not q hat over 2, sorry. So you do the exercise with the Gaussian integration formula. It's very simple. Square root q hat z xa minus q hat over 2 xa squared, and I have a sum over a there, and I have an integral with respect to z. This is my auxiliary variable, okay? This is my Gaussian integration variable, which is just a standard Gaussian. Okay, you can just check, you do this integral of this exponent, and you will recover this, which is this, okay? So it's a trivial exercise. Perfect. And now I claim that we are in a position to take k going to 0. Okay, so it's the final step and we're done. So now we can finally take k going to 0 in a q hat divided by k. So let's do that. So I claim that the final formula is limit. So the final formula is given by the limit when k goes to 0 of this plus this. And here you see you have a form log of an expectation of an integral to the k. Because you see this is fully factorized to the k plus 1, sorry. A equals 0 to k plus 1. And this sum goes from, I can factorize my product, takes everything here. So this is just a single integral log of expectation with respect to z of a single, again, one-dimensional integral. Now it's really one-dimensional, it's not k plus 1 dimensional anymore. A single x to the k plus 1. Okay? So now you see we obtain an expression which is not only factorized over the real index I, which was going to infinity, but now we have also managed to linearize with respect to the replica index using this replica symmetric ansatz. And now I claim that if you have an expression like log 1 over k log of an expectation, let's say with respect to z, of a function of z to the power k plus 1, the limit of this when k goes to 0 now makes sense. And this is equal to expectation of log of this function. So you see, we use again the replica trick the other way around. Here we have k plus 1, before we had k, but you can, sorry, excuse me, make a mistake. Yes, I'm sorry. The replica trick otherwise would be wrong. You can check that this is expectation. Yes. Z, f of z, log of f of z. Because you see you can write this as f of z to the k times f of z. And at the end, this one will go out, and the log will be reconstructed by this, by the replica trick. So it's again by Taylor, can be verified by Taylor expansion. So you can use this formula, it's like a replica trick again. And if you do so, what you get the final formula. We're done. So the limit I have 5 minutes left, so it's good. So the limit, I summarize, limit when n goes to infinity of 1 over n expectation of log of the partition function of y is given by the limit when k goes to 0, limit when n goes to infinity, 1 over nk log of expectation of z to the k, which ended up being limit when k goes to 0 of 1 over k our action excuse me. Okay, which gives extremum with respect to q and q hat, where q and v hat, which are these four quantities, v, q, and v hat, q hat. Yes, so in the notes I have not written the v and v hat because excuse me one second. Yeah, excuse me, the v and v hat never appear actually, because you see the only terms that appeared is for A different than B here. So I never need to consider the diagonal of this matrix. So this v and v hat at the end do not appear in the expressions. You can check. There is no v and v hat. Q hat over 2. I will write this below. And here it includes also an expectation with respect to x star drawn from the prior. So here, yeah, there's been a simplification. Okay, using this trick here, which is again this replica trick, you obtain this expression. So this is the final formula. It's the replica formula. So the one I've shown at the beginning of the course, there was no q hat. There was only this parameter q. But actually now if you solve the fixed point equation, the saddle point equation, so let's call all this function f replica symmetric of q and q hat. Now you need to find the extremum. So you need to write the gradient with respect to q and q hat of f q hat equal to 0. You need to solve these equations. And what it will give you, you can just write the gradient equal to 0. It will give you q hat equal to lambda q. So you already see that even if when we introduce delta functions, this q hat were potentially complex variables, the saddle point equations tell you that this q hat is just proportional to q. And q is clearly a real number. It's the overlap. It's an angle. So at the end, everything remains real, okay? And if you plug this into this function, it becomes just a function of q. And this function of q is the one that was given at the beginning of the course. It's the replica formula, okay? Now, if you do instead, so this follows, this equation follows from the partial derivative with respect to q. And the other equation with respect to q hat gives the equation that Q verify the self-consistency equation that I gave at the beginning. We have the denoising, the scalar denoising problem with the signal-to-noise ratio lambda Q that appears. Here, if you go back to the beginning of the lectures, you realize that this object that appears in the replica formula is related to the mutual information of the scalar denoising problem, where the signal-to-noise ratio is this Q hat, the Fourier conjugate, which is equal to lambda Q. Okay? So that's it. We obtain the replica formula. Okay, now you solve this stationary conditions, this equation, which is now just a function of Q, because I removed the Q hat thanks to this equation, and you obtain the curves that I've shown at the beginning. Okay, that's the replica symmetric prediction for the MMSE. And then, of course, you should be doubtful about all this. I've made many weird things, many assumptions that I could not justify, and you would be rightful to doubt. But I can tell you that now there are methods to prove that the final result of this method is indeed rigorously correct. And yes. Hello.
Hello.
I'm hearing.
You are audible. Hello.
You are audible, yeah.
Achha.
I could hear you, yes. Okay, you have a question?
Please share your question either on a chat box or directly here.
Say it again. Okay, I don't think it was a scientific question, so it was.
So you can continue. Please continue, sir.
Okay. No, but okay. Yes, so I'm done for this course. So basically, that's it. That's the statistical physics derivation of this replica formula. So it looks involved, but I can really assure you that if you accept these heuristics that I've given you, all the remaining steps are just Gaussian integral or completing squares. It's from the algebra point of view, it's pretty simple. What is not so simple is these commutations of limits between the replica limit and the large size limit. Then to understand what this replica symmetric ansatz means and connect this to the fact that physically it means that the order parameters concentrate onto their mean. So these are the important points, but the computation is pretty simple. So it's in the notes, and I'm pretty sure that most of you can repeat it. Okay, so thanks to that, now we have a complete theory for the spike-Wigner model. We have computed the free entropy, which is basically the mutual information up to an additive constant. You can see in the notes the link between free entropy, which is essentially the Shannon entropy of the problem, and the mutual information. We discussed this at the beginning. So we have this mutual information. By the IMMSE formula, we have the MMSE. So now we have a prediction for the minimum mean square error reconstruction of the spike in this problem. We have analyzed also the reconstruction performance of spectral PCA. So we have an algorithm and the Bayes optimal limits. Okay. The last thing I will discuss a tiny bit tomorrow is this Bayesian algorithm, which is approximate message passing, which allows to estimate the Bayes optimal estimator, but without having to really sample the posterior distribution in a smarter way. Okay. But basically now we have already a good strong theory, a good chunk of the equations we need to understand the phase diagram of the Spike-Wigner model. Okay. Perfect. So tomorrow I'll start with discussing for an hour this AMP algorithm. I won't do much derivation. I will just give you the idea behind it, and then I will spend the remaining hour and 2 hours, the last 2 lectures, to discuss many other examples of problems in computer science, in inference, in coding, in machine learning, where these techniques are useful. Okay. Perfect. So if there is a question, please go ahead. Otherwise, we'll meet tomorrow, I guess.
Yes. Any questions from the audience side? I think no one is having any question. So thank you, sir. We'll meet tomorrow at 11:30.
Thanks a lot. Goodbye. Have a good day.
Okay. Thank you, sir. Tomorrow 11:30, right? Okay, sir. Okay.
Yes.
Thank you, sir.
Bye.
Thanks a lot. Goodbye.